Good afternoon. Today we'll be presenting our group project on part-of-speech tagging. This is Group FT19. This is an overview of the team and their contributions. So what is pause tagging? It is the task of assigning a grammatical category, such as noun, verb, or adjective, to each word in a sentence. So as shown, the word the is being tagged as determiner, while jumps is tagged as a verb. And this is a foundation task of NLP. When we talk about pause tagging, we have to address three core problems. The first is lexical ambiguity, which is a problem where each word can have different pause tags depending on the context. OOV, or out of vocabulary words, are words that are unseen during training. And the third, the trade-off between accuracy and computational efficiency. We use the Brown corpus with universal pause tag set. So it has over 56,000 sentences, 1.16 million words, and 12 tags. As the distribution shows, noun dominates, which will influence the model performance across all tag categories. For our modeling approach, we implemented models in increasing complexity. Naive Bayes serves as our context-aware baseline. HMM introduces sequential dependencies via the Viterbi algorithm. The CRF leverages rich features in a discriminative framework. Lastly, BiLSTM learns dense representations from both left and right contexts simultaneously, and it represents our neural tagger.
Hi, I am Mabel. I will be presenting our naive Bayes classifier model, which is our baseline model. We used sklearn's categorical NB, which applies Bayes rules across the three integer encoded context features. It assumes feature independence, but the assumptions still use a strong baseline given the informative trigram context. The data was split at the sentence level using an 80-20 train test split to prevent any data leakage. For out-of-vocabulary handling, OOV, we built vocabulary exclusively from training data and substituted unseen words with a special UNK token, with separate encoders for each feature column. Rather than tagging words in isolation, we engineered a trigram context feature vector, capturing the previous, current, and next word. This contextual modeling was critical. Without it, accuracy was only 21%, adding the trigram window pushed it to 95%, a gain of 74 percentage points. Sentence boundaries are handled with BOS and EOS padding tokens. The model achieves 95% overall accuracy, with training taking 0.79 seconds and inference just 0.14 seconds. Closed class text like punctuation, determiner, conjunction, and adposition score above 0.94 F1. The two weak spots are num, where recalls drops to 67% due to numeral ambiguity, and the X miscellaneous text, which has only 7% recall, largely because it represents under 0.1% of the corpus. The confusion matrix confirms the diagonal is dominant, but highlights four key error pairs: noun with verb, adjective with noun, particle with adposition, and adverb with particle boundary ambiguities. OOV words disproportionately affect proper nouns and numbers. The X tag failure stems entirely from severe class imbalance. Almost all X tokens are misclassified as something else.
Hi, I am Mya, and I'll be walking through the implementation of the HMM for our project. Here are all its stages. The first one is data preparation, followed by the train test split in a way that preserves the tag distribution across both sets. The next one is OOV handling, after which we do the training of the HMM, followed by the use of Viterbi algorithm, and lastly, we evaluate the performance using accuracy on the test set. We use an 80-20 sentence level split with random stage 42 for reproducibility. In terms of data preprocessing, for OOV handling, we introduce a UNK token to deal with words and sing during the training. Any word appearing only once or fewer in training gets replaced with UNK. To estimate the HMM parameters, we first compute the three count matrices from the training data: INIT, transition, and emission. We also apply the add K smoothing with K equal to 0.001, adding a small constant to every count before normalizing. The Viterbi algorithm is used to find the most expected POS text sequence for a given sentence using dynamic programming. It works in three steps. First, initialization computes the starting probabilities for the first word. Then, recursion moves through each word, selecting the most likely tag based on the previous stage. And finally, backtracking traces back through the stored parts to recover the optimal text sequence. As for performance summary, the HMM model achieved an overall accuracy of 95.83% with strong precision, recall, and F1 scores around 0.96. It performed very well on frequent text such as punctuation, conjunction, and determiners, achieving near perfect F1 scores. However, performances were weaker on rare text such as X, which had a much lower F1 score. But overall, the results show that HMM captures the sequential structure effectively but struggles with rare cases.
My name is Cho Thin, and I'll be presenting about the CIF model. Here is the stages from the beginning to the end. For data preparation, we use the same dataset, the brown corpus. Unlike deep learning, CIF rely on manual feature engineering, and we extract about 26 feature per word, like focusing on morphology, like prefix suffix to handle unknown word, and context, like previous or next word to capture grammatical flow. This is where the model form is intelligent. For training, we use 80-20 split, like which is standard. We optimize the model using the limited memory BFGS optimization algorithm, which convert efficiently for large feature set. We also apply elastic net regularization to prevent the model from memorizing the training data, which cause overfitting. For prediction, the model used the VTB algorithm. Instead of tagging word independently, we find a globally optimal text sequence for the entire sentence, ensuring grammatical consistency. So to measure success, we use weighted F1 score since our dataset is imbalanced. This metric gives a fair performance measure across all categories. Moving to the result, our approach was highly successful. We achieved an overall accuracy of 97.94%. Here we can see, and training time at 5 minute, real-time inference at like 3 sentences per second. So this shows both accuracy and efficiency. Looking at the performance pattern, the best we achieved nearly perfect score, like F1 almost 1 on phrase synthetic tag. And the bottleneck is the ACE tag with only 329 examples. The model struggled to generalize, so resulting in an F1 of 0.54. Finally, our error analysis showed the model's weakness is linguistic ambiguity, not random noise. Our top error type is verb to noun confusion, which is almost 12%. This happens with gerund, like the word which look like Bob, but mentioned as noun. So future improvement for this is using word embedding. It will solve the semantic gap, and I will pass my time to Haven.
This is Thinzar Myo, and I'm going to present about BiLSTM and the summaries of our group project. So the model we built is a bidirectional LSTM. We split the data 80-10-10 at the sentence level with a fixed random seed, so everything stays reproducible. The vocabulary comes purely from the training data, and any other words that appear less than twice get replaced with a UNK token. So the model is ready for the words it's never seen before. Before anything hits the model, every sentence goes through 5 steps pipeline. Lowercasing, mapping words to the integer, swapping rare words for the UNK, padding into the uniform length, and wrapping into the PyTorch dataset. The training later shuffle every epoch to help the generalization, and while validation and test loaders stay fixed for the fair comparisons. The architecture uses 100-dimensional embedding feeding into the two bidirectional LSTM layers, 128 units in each direction, giving us 256 features per token. We added dropout at 0.3 to prevent the overfitting, and a final linear layer mapping to the 13 output classes. We trained with Adam, gradient clipping at 5.0 over 10 epochs. So how did it perform? 97.37% overall accuracy. Common tags like determiners and punctuation hit an F1 score of 0.99, basically, which is perfect. But the real highlight was rare tag. Ace tag recall jumped from 7% all the way up to 52%, and the number tag recall from 67% to 92%. That's where the bidirectional context really proved its worth. So where it struggle is a raw ambiguous words, noun versus verbs for the words like book or ran, adjective versus noun for the participle adjective, and particles like app mixing with the adverbs. The ace tag still beats into the other classes due to the imbalance. That said, the model coverage cleanly, no overfitting across all the 10 epochs. The loss curve are smooth and steady throughout. Stepping back across all models, naive Bayes at 95%, HMM at 95.83%, BiLSTM at 97.37%, and the CRF at the top with 97.94%. The BiLSTM's biggest weakness is the training time, roughly around 60 times lower than the baseline, and it doesn't have a CRS decoding layer yet, which is honestly the most obvious thing to add and likely where the biggest remaining gains are. So, let's wrap up. 3 things stood out to us. The CRF was our best overall model, hitting 97.94% of the accuracy, and training 60 times faster than the BiLSTM. Moving to the sequence model, in general, give us a solid 2 to 3% boost from the capturing context. And one thing every model struggle with is that the ambiguous words like walk or major, that's not really a modeling problem, that's just how the language works. And that's exactly what pushed us into the future work. So where do we go from here? The most immediate step is combining the BiLSTM and CRF together, using the BiLSTM learn feature and the input into the CRF. After that, we want to bring in transformers like BERT, where we are all expecting to hit above 98.5%. On the training side, Ali stopping for the BiLSTM and more iteration for the CIF. And the longer term, testing across different domains and eventually deploying the best model as a live API, targeting under 50 milliseconds per sentence. So let me end our group presentation here. Thank you for your attention and listening.